I forgot to turn my microphone on, so I'm just going to have to narrate this. We'll see how it goes. It's not going to be live narration anymore. It's going to be narration after the fact. So we have an annulus with an inner radius of R1, outer radius of R2, a uniform positive surface charge density sigma. That's the charge per unit area. So can we use Gauss's law to find the electric field at some point on the x-axis? So the center of the annulus, axis going through the center of the annulus is at the x-axis. If we pick an arbitrary point along there, can we find a Gaussian surface that will make Gauss's law easy to apply so we can find the electric field along the x-axis? That's the question for you. See what your answers are. So the main answer is we'll need to do an integral, which adds together all the components. Certainly a significant number still answering that Gauss's law will work. So let's do a quick sketch. This is a cylindrical kind of problem, cylindrical in that there's symmetry around the axis. So I could think of a Gaussian surface that's cylindrical, which is what I've drawn there. And the problem is, again, like we've seen before, is that the electric field due to that positively charged annulus is going to change the field. The field direction is not always going to be perpendicular to the Gaussian surface. It's not the same magnitude, not the same direction, so Gauss's law is going to be hard to use. Really impossible to use. When the electric field varies over the surface, then that integral in Gauss's law is hard to do. So let's get rid of this. Forget about Gauss's law. Add up fields due to differential pieces of the annulus. Calculate it for one differential piece. We'll choose as our differential piece. So there's the annulus again. As our differential piece, we'll choose a ring, a very, very thin ring out at radius r. I'm drawing it out at radius all the way out, but it could be anywhere in the annulus. A very, very thin ring at radius r, capital R, away from the origin, and with thickness dr. So there's the picture. This tiny ring that I've chosen, the outer piece of the annulus, will have thickness dr. I call it d little r here, but I'm going to have to change that to d capital R. So let me just jump ahead to where I think I've already done that. The area of the ring is, of course, the circumference times the thickness. So 2 pi r times dr is dA. To get the charge on that ring, I take the charge per unit area, multiply by the area. In other words, take sigma, multiply by 2 pi r dr. And you can see why little r is an inappropriate variable, because little r is already up here, and that's the distance to the point from the ring. And probably right now, as I was doing this in lecture, I recognized the problem and hopefully will, yeah, there you go. Hopefully it will change. So it's hard to erase here. Draw that outer ring again, the outer part of the annulus, and call that capital R, and call that d capital R. 2 pi capital R times dr is dA. And then I'll integrate capital R. Once I write the equation, I'll end up integrating capital R from R1 out to R2. And the reason I wanted to get rid of the little r is that little r sits up there in E, the electric field due to a point charge. The magnitude of that little r is the distance from the ring to the point of interest. The point of interest is x. So from the ring to the point of interest is a vector that looks okay. There's the electric field from this little tiny piece of the ring to the right. A little tiny piece of the ring to the left produces that electric field. You can see that the radial components of the electric field are going to cancel, the x, the y, and z components, and we're only going to end up with an x component of the electric field. So when we write down the differential electric field, we're going to have to make sure that we're just calculating the x component of that. And if I remember correctly, I erased a bunch of stuff and had to rewrite this whole thing to get something that we could talk about. So, okay, so here I'm drawing the actual vector little r. Little r is from the ring, whatever interesting point on the ring I care about, to the point up on the x-axis where the field actually is. And little r depends on capital R and depends on x both. So Pythagorean theorem tells me what little r is. I can write the angle also as a function of capital R and x, and end up with dE in the x direction by integrating what I'm calculating here, this dE, integrating it from capital R equals capital R1 to capital R equals capital R2.